I will be talking about our experiments about color data augmentation for metastasis recognition and classification using deep learning approaches. I'm a computer scientist, so basically I developed some approaches, or I use some well-known approaches to study this kind of images. So basically, what's the problem that we are facing? The problem is to recognize and classify breast cancer metastasis images, which is it's a difficult task itself. But part of that, the size of the images also is another problem. But the main problem of this, as my colleague was telling before, is that the images can be very different from, especially from different laboratories, even if the specimen is similar or we are referring to the same tissue type. The variability of the stainings and or even the staining kits may produce different colors, which can then affect the colors at the time of the acquisition. And when we try to train a deep learning algorithm, this could be potentially biased to one or the other stainings or staining kits. So basically what we use for to approach this problem itself, so we use some deep learning methods based on convolutional neural networks, which are basically biologically inspired neural networks, so virtual networks that apply to they can apply to visual visual problems, so like image recognition or video analysis or natural language process or medical image analysis, as in our case. The architecture of the typical architecture of the CNN is composed by a combination of layers, which are basically the convolutional layer, the pooling layer. So the convolutional layer basically filters the data with a kernel and produce some filtered values. The pooling layer is like an undersample layer, and the fully connected layer, which connects all the results one to the other. This is normally used in the convolutional neural networks in combination, or we have a stratification of layers, which may make this network deeper and then even more solid for our purposes. So what we used for in our experiments, we implemented it using this library called Café, which is basically a deep learning framework and implements different neural networks, and especially it supports both CPU and GPU acceleration libraries, since the problem to face is quite big and implies a lot of computational power. Then we decided to implement in a GPU style. So just a very quick recall to two neural networks that we are using in our project, that are the VGG16 with 16 layers and ResNet 152, which is these two particular neural networks have been the best performing networks in image recognition in a challenge some years ago. So we decided to combine their power to try to solve the problem of the recognition for the metastasis. So as was pointed before, one of the problems that we can face is is a bias during training in a neural network. Therefore, we can think about to create some let's say synthetic images to augment the type of images, or to augment the variability of the images that that our neural network can handle, using different methods. Like there could be kind of geometrical ones, like the I don't know if you can really see the differences here, especially in the color image, but at least here we can see that there is a rotation 90 degrees. This is the original image. You can point this reference point and see that it's here right now. So it was a rotation, a crop of the image, and we basically focused our method to also introduce new images, create new images by changing the colors. In this case, I make the examples of hue, saturation, and value, so the images are no more RGB in the RGB space, but in the HSV space. As I said, our method basically uses the VGG16 for the beginning, for the first part of the training, where we also change the images, or we also change the color of the images. So as I said, we convert every tile that we give as an input to HSV color space. Then we modify each of these tiles by 10% in the 3 channels of the HSV space. So we generate for each tile, we generate other 6 tiles, and we use all of them to train the VGG16 net. And then we predict the results over that, and using these results, we retrain the ResNet 152 to have the final results. So we use that kind of coarse to fine approach. The datasets where we applied our method basically was taken from the Chameleon 16 challenge, which gives over 270 whole slide images, both of tumor or normal, for training, and 130 whole slide images of tumor for testing. The evaluation was taken also directly from the Chameleon challenge. Basically is the identification of individual metastasis with a FROC value, with a free response receive operator characteristic curve, and also classification of metastasis was evaluated by the AUC curve. We also implemented two different models, one with and one without core data augmentation, so we could also directly compare to our previous work the increase of our results. Okay, we implemented this on a Xeon machine with 16 gigabytes of RAM, running over an NVIDIA XP Titan, and the software was implemented in Python, and GPU implementation using the Caffe library. So quickly the results. So these are the results taken from the calculation of those values that I introduced before. So we can see the FROC curve giving a score of more than 50%, and the AUC curve, so classification of metastasis, of more than 90%. For comparison, the previous work without the color data augmentation gave a score of around 38% and 89.75%. Therefore, we can immediately see the increase of the quality of our results using the color data augmentation. So to conclude, we could see some some significant increase in the score for the identification of the metastasis, and also a small increase in the classification of metastasis. Our future steps will be to extend this data augmentation, so consider a better optimization for the color data augmentation, and introducing also the geometrical data augmentation, and test them on different data sets, including other challenges like Chameleon 17 or HR 18. And the main objective is to test this on real data sets and see how good it works. So just want to acknowledge my colleagues from Institute of Pathology in Udine, in particular Prof. Carla Di Loreto, and the NVIDIA Corporation, which donated us the Titan XP graphic card to research purposes. Thank you very much.
We have time for one quick question. Well, I have one thing to ask. So the stains are actually, I suppose in the case of H&E, it's two separate stains on a single section, and the stain variability of the two could potentially be independent. Have you considered separating out the stains and treating them individually?
Yes, especially focusing on the hematoxylin that could be significant in some cases, but we are just starting this investigation, so we can consider even that to make it more robust.